Hello everyone, we're Group 5, Group 7, and the topic we're presenting today is DirectIR training free enhancement for diffusion-based image restoration by contrastive guidance. Let me briefly introduce the task we are addressing first. The task we are addressing is all-in-one image restoration. The main goal of image restoration is to utilize deep learning methods to restore a degraded image into an undamaged one. In previous research, methods usually focus on single type of degradation, which means that we'll have to train multiple models to handle different types of degradations, as shown in the left picture. Although single degradation restoration has achieved a quality result, images in the real world often suffer from multiple and overlapping degradations. Thus, recent studies turn into all-in-one restoration, which use a single model to simultaneously restore multiple types of degradation. For example, PromptFix, an all-in-one instruction guided diffusion model designed for low-level image processing tasks. Recently, the Stable Diffusion model has demonstrated exceptional performance in high-level image processing tasks, such as image generation, and has shown remarkable controllability through human instructions. PromptFix aims to transfer this capability to low-level tasks by fine-tuning the Stable Diffusion model on extensive low-level task datasets, enabling it to restore various types of image degradations while allowing control via text prompts. Additionally, PromptFix leverages the VLM to generate auxiliary prompts, which include semantic annotations and detailed descriptions of image degradations. This design enriches the text prompts and enhances the model's task generalization capabilities. However, after conducting experiments using their model, we identified some challenges in their approach. PromptFix sometimes fails to align text prompts and result images, which limits its overall reliability. It also struggles to restore images effectively, particularly when dealing with out-of-distribution data. For instance, as shown on the left-hand side, the deblurring results produced by PromptFix are suboptimal. Similarly, on the right-hand side, the model fails to deliver satisfactory outcomes for the task of low-light enhancement. In our project, we address these challenges and propose a solution to improve its performance. Let's go into our main approach now. This is the overall pipeline of our main approach. Fine-tuning or retraining the PromptFix model requires significant computational resources and risks affecting its pre-trained knowledge. Therefore, instead of modifying the model itself, we leverage the pre-trained PromptFix as our base model and introduce a loss function called textual contrastive loss, which can be seamlessly integrated into every sampling time step. The main idea of the proposed method is to address the issue where the model sometimes fails to respond effectively to text prompts. To fully utilize the robustness and potential of text guidance, the loss leverages text embeddings and image embeddings in a contrastive loss framework. This approach guides the diffusion sampling process, ensuring that the distribution of the degraded image transitions smoothly into the distribution described by the user instructions. Now, let's dive into the design of our textual contrastive guidance. First, we take the step result from the diffusion model and decode it into the image space. At this stage, we get an image from a specific diffusion step. Our goal is for the loss to guide the next step closer to the target distribution, which is the user's instructions. To achieve this, we calculate the CLIP similarity between xt-1 and the user's instructions called global loss. This effectively provides a guidance to refine the latent representation. To further enhance the results and address issues such as mode collapse and corrupted image quality, we introduce the direction loss. This loss leverages the residual difference between the input image x0 and xt-1, comparing it to the residual between the user's instructions and the VLM degraded description. By aligning these residuals, the direction loss ensures consistency in the CLIP embedding space between text and image pairs, providing a more definitive optimization direction. Finally, we combine the global loss and the direction loss, compute the gradient, and use this gradient to guide the latent code. We can view the entire process as guidance within the data manifold, aiming for the loss gradient to direct the distribution flow toward the target distribution, aligning it with the user's requirements. Let's see the results of our method. We evaluate our method on four different datasets and tasks: synthetic rain datasets for image deraining, LOO for low light enhancement, GoPro for remove motion, blur and snow cityscape for desnowing. For evaluation, we employ three commonly used quality metrics: PSNR, SSIM, and LPIPS, as well as three human visual quality metrics: MEUSIQ, MEN-IQA, and CLP-IQA. The restoration metrics evaluate image quality by analyzing pixel level differences, structural integrity, and similarity between the predicted image and the ground on truth. In contrast, the human visual metrics assess perceived quality by aligning the image with human visual preferences and perception. Together, these metrics offer a comprehensive evaluation of both objective fidelity and subjective quality, ensuring a well-rounded assessment of restoration performance. Our results achieved better scores across most metrics compared to the original Promptifix model. Notably, there were significant improvements in metrics related to human visual perception. Below are some visualizations of the results for light image enhancement. We can observe that the Promptifix fails to enhance the brightness of the image, whereas our method successfully improves the brightness without requiring additional training. For motion blur image restoration, our method achieves notable clarity and accuracy, effectively preserving fine details when compared to Promptifix. While our approach produces cleaner results overall, it still faces challenges in fully recovering fine-grained details, such as text on license plates. In the desnowing task, our method delivers clearer and more natural outputs by significantly reducing noise and enhancing visibility. While Promptifix performs well in handling smaller snowflakes, it struggles to effectively reduce larger ones. In contrast, our method demonstrates the ability to handle snowflakes of all sizes, providing a more comprehensive solution. Our method can handle out-of-distribution data that includes degradations originally addressable by the Promptifix model, enabled by the robustness of text-based guidance. For the deraining results, our method did not show significant improvement compared to Promptifix. Although our method can handle out-of-distribution data, unseen degradation patterns, such as rain, remain for a challenge for restored degraded images. Our method uses a weight parameter, lambda, to balance the impact of contrastive guidance. We noticed that too much gradient guidance can cause artifacts. This happens because overly strong guidance disrupts the original diffusion sampling process, making it lose its ability to guide properly and drift toward the wrong data distribution. On the flip side, if the guidance is too weak, our method's impact decreases, leading to poorer restoration performance. Through our experiments, we found that setting lambda to 0 during time steps between 400 and 500 provides the best trade-off between quality and artifact control, resulting in the most stable and optimal outcome. Finally, let me quickly summarize our contribution and limitations. Our method identifies and addresses the issues in Promptifix, achieving significant improvements across various restoration tasks without additional training. Moreover, It is compatible with various pre-trained diffusion models, making it a promising solution to enhance the performance of different base models. Despite the advantage, our method fails to restore the unseen degradation types such as rain. We believe incorporating generative priors is a promising direction for addressing this limitation.